Okay, so we looked at algorithms in the last module, and one of the example algorithms that we were looking at runtime for was search. And search is a really a common problem in most programs and most applications of computer science. The idea is we have a list of things, whether they're strings, integers, floats, anything, and we need to search a list to try to find the value. And so in this module, we're going to go through, it's going to be a little bit more code than some of the other slide-based lectures, but we're going to be going through a few different implementations of searching through a list of numbers. And again, we're not going to look at the Python in command right now. We're just sort of trying to get an idea of really how this works internally. So all of the things that we'll deal with is integers, but this would work and extend to pretty much any data type. Okay, so searching lists. One of the things that, based on the discussion from the last module, is that depending on the algorithm, we can probably expect that there's going to be a pretty good runtime difference with these different algorithms. So I'm going to first start off with implementing a standard, just kind of linear sort search. But one of the things that I'm going to do, I'm going to spend some time developing sort of a test case program because I want to um, move on past the standard linear search and be able to compare and contrast the different algorithms that we use. So the first thing that I'm going to do is I'm going to write a program that first generates 10,000 random numbers. So it's a fairly big number. It'll take a non a non-zero amount of time to actually run this. So we'll generate 10,000 random numbers between, let's say, 0 and 10,000 or so, or maybe 100,000. And then we're going to generate another set of 10,000 search values. So this would be values that we're going to search for. And then we're going to actually run 1,000 or 10,000 independent searches of our random numbers that we generated in the first case. And then we'll report the total search time, or we can report the average or the total search time. It really doesn't make a difference. And then once we have that, we can start to build on that and try different algorithms and see what we can do. So let me switch over to the code. And I'm going to do that just that. I'm going to first start by writing a variable to, to, to represent the maximum, the number of search values that we're going to generate, the number of independent searches that we're going to make, and the actual maximum number. So this one variable is going to control them all. And if we run into any bugs or anything like that, I can change this, down to 10 or something like that, and print out all the results, and it'll be manageable. And then I can move it back up to 10,000 once I know it's running correctly. So first thing is I'm going to create my list of actual values that I'm going to generate. So these are going to be my random numbers, and I'll generate 10,000 in this case, or GenMax, random values between 0 and 10,000. So for I in range 0 through 10 GenMax, um, I'm going to just append a new random value. And so we haven't really talked about random numbers all that much, but the random library, and let me import that. The random library, and we'll talk more about this when we cover simulations later on in one of the last modules of the course. But the random module allows you to generate a somewhat random number. And I say somewhat, it's not perfectly random. Nothing in a computer is perfectly random, but it's going to be different every single time you call it and every single time we run the program. So if I say random randint, I can ask random for an integer between some minimum and max, and it'll return a sort of undetermined value, some random value each time. And just so we can get an idea for this, let's bring this down to 10 so we don't print out 10,000 values, but let's just print out the list so you get an idea of what we're going to see. Okay, so I generated 10 random numbers, and I see that they're they're not in any order, and I've got some repeats clearly. If I run this again, I'm not going to get the same numbers, so it's a good nice mix of different numbers. So I'm going to want to generate 10,000 of them. Okay, so I've got my data set. This is the thing that I'm going to search. And now I'm going to generate, I always want to, I'm going to generate a list of numbers that I want to actually search for. So I'm going to call that keys. And it's basically the same idea. So for int I, or for I in range, 0 gen max, it's essentially the same thing, but instead of data, I'm going to be appending it into keys. Right? And again, let's bring this down to 10 and print them all out. Oops, keys, not key. And it looks like I did that in a couple places. Okay, so the idea behind my program is that I'm going to generate, this is my data that I'm generating, and I'm going to search for the number 6, and then I'm going to search for the number 5, I'm going to search for 0, 6, 7, I'm going to search for all these numbers over and over again. And I don't really care what the numbers are, I'm really going to be measuring how much time it takes me to actually search for these values. Before I go much further, I violated one of my rules of do not repeat yourself, right? You can kind of see that this is essentially the same code. Let's make a function, generate random list that accepts a maximum and returns a random list. And that way we don't have to repeat these for loops. So result equals a list. Okay, so when I call this function, I'm going to generate a random list. I'll pass it in maximum. I'm going to generate all those numbers, and then I'll return result. And now data and keys is really just generate random list. Okay, so I like that better. That's a little bit more succinct, and I can kind of move that function away from my main part of my code. Nothing else. Turn result. Nothing else will really change here. Let's test it to make sure things look right still. And again, of course, it's not the same numbers. Okay, so let's let's implement the actual code that will start to search things. So I'm going to create a simple linear search function, and I'll call it linear search. That'll take a list of data and a value that we're looking for, maybe key, and it's just going to return true or false, whether or not it finds it. And again, this is just going to be a simple linear search. So there's not a whole lot going on beyond a simple loop through our data. So I in data, if I equals the key, return true. And otherwise, just keep going. And if I make it all the way through my for loop, return false. Okay, so that'll tell me whether or not I actually found the value. And now down in main, instead of starting to print out all the, well, actually, I'll keep the print out here. I'm going to actually call this, and I'm going to call it for every single key that I've generated. So for key in keys, I don't care whether it, well, actually, let's keep track of how many actual things we found. We'll call it hits, and I'll say if linear search for my data key equals true, then hits plus equals 1. I'm searching and finding each one, and then that's it. All right, so let's say found the number of hits. Okay, so let's run it. Okay, so I found 6 hits, and let's just do a little sanity check here. 4 was not found, 3 was not found, that's not in here. 9 is found once, so that's 1 hit. 10 is 2 hits. 6 is not in this list. 2 is not in this list. 5 is found, 5 is found, so that's 4. And 9 is found, and 9 is found. That's a total of 6 hits. So 6 out of the 10 keys were actually found. And sure, some of them are repeats, but my algorithm isn't sort of learning or anything like that. So they were independent searches each time. So I found a total of 6. So I'm confident that at least my search function's working. Okay, so let's start to think about how we can make this a little bit better. So if we know nothing about the data, so we have a truly completely random list, the standard linear sort is pretty much as good as it gets. We can't predict the location where the key might be. We don't know anything about the location where it could be, so we must look at every single element before deciding whether the key was not there. And so if you're paying attention to the last module, you probably know where I'm going here. And what if we knew that the list was already in order? What if it was a sorted list? And if it was a sorted list, we actually have some more options. Ordered lists, by the way, are not very uncommon. So you might think, well, this is kind of a pretty big caveat, but it's not. We encounter sorted lists lots of times in programs. It's fairly easy to keep a list sorted if we're only changing it every so often. So it's a pretty valid constraint. So let's say we were looking for the number 15. If we were to do just a kind of a blind search, if we didn't assume that there was any order to any of these numbers, we'd have to go all the way through the list, and we'd look at every single one before we were able to determine that 15 did not exist. If we use that knowledge, we would look all the way through up to 14, and then the very next number we looked at would be 17. So we're scanning left to right. But because we know that this thing is ordered, as soon as we find that 17, it's actually kind of silly to keep checking the rest of the numbers. We don't have to compare and loop around and look at 18, 21, 25, 28, and 29, because we know that 17 is bigger than 15, which means 15 would have had to come before that value. And that's a win, right? Anytime that we can stop early, we can arrive at the solution faster. That's pretty advantageous. So it turns out that's really easy actually to implement. So let's go back and let's generate an alternative. Okay, so linear search ordered. And I'm going to say if I is equal to the key, return true, else if the particular I value that I'm looking for in data is greater than the key, I'm going to return false right away. I'm still going to have this false because if we go back to the loop, if I was looking for, let's say, the number 30, I would have never encountered a value that was greater than 30. So I still need to deal with the situation where I finish the entire loop without finding a value. All right, so I want to test the linear search and also the linear search ordered. First off, the data. I'm going to actually sort this. So Python actually has a built-in sort function. We'll talk a little bit more about that in the next module, but I'm going to sort the data ahead of time, and I'll print out the keys. And I'm also going to test now individually the linear search ordered. All right, so let's give that a run. All right, so first off, notice that the data now, there's still random numbers that were generated, but they are in order. When I calculated, or when I called the linear search, I'm still searching for the same numbers. The linear search does not take into account that it's sorted, so we're not saving any time by the fact that the data is sorted. It found 6 elements. The linear search that knew or is aware that that input is sorted found 6 too, which is good, right? So certainly there would be something vastly wrong if these numbers were different. But we haven't really kind of completed that comparison. which one is better, which one, maybe how much is one better than the other. Before doing that, I want to take, I write a little code, and you'll notice this, I write a little code and then I improve it. I write a little code, make sure it works, and then I try to improve it. Right off the bat, we can see that this is virtually the same as this code. And so the only difference here is that I'm calling a different function. So I want to try to take this code and generalize it. So I'm going to go all the way up to the top, and I'm going to call this run test. And it's going to accept data and my keys, and it's going to create a variable called hits. It's going to go through all my keys, but I don't want it to call linear search. I want it to call something else. I want it to call something that I can control. And one of the things that we skipped over when we talked about functions in the textbook was that functions can be functions are objects, and function names, in fact, can be variables. And we can pass function names into tests, into functions, which allows us to write a function that can sort of call different functions based on what the parameters are. And so what I'm going to do is I'm going to say, I'm going to call it algorithm. Right, I'm going to make a parameter called algorithm here. Right, and if you notice that linear search, ordered, and linear search, they're exactly the same functions in terms of their parameters. They just have a different name and a different code. So I'm going to have my run test function keep track of how many hits we get. It's going to search through all the keys, and it's going to call whatever algorithm it is that we pass in. Instead of printing it out, I'll just return hits. Now down here, I'm going to say run test, and I'm going to pass in data and keys in linear search. Right? And so now when I call run test, the function linear search will be passed into this function and now be called algorithm, and I can call it just like I'd call any other function. So this is called functional programming. It's kind of functional programming light. There are other languages that take this to a much more significant extent. It's a really nice way to write some generalized code in Python. Okay, so and let's make these print statements a little bit better. Using linear search. Okay, and we'll do the exact same thing with ordered. Okay, so our main program is certainly staying kind of succinct. All right, so I said 5, found 5, and again we see that number agreeing. That's good. Okay, so we don't really know necessarily. We have an intuition that one is better than the other, that the ordered list one is better, but we don't really have any way of really measuring that. And if we look at both of these functions, our first idea of, what's the big O notation? What's the complexity? Well, the thing is they both have for loops. They both loop over to data. The ordered list has a slightly better average case. Every once in a while, or hopefully most of the time, it should be able to finish early, should be able to figure out that it can't find the number fairly quickly. But that's only for the number of misses. So if we were imagining a situation where we always found the number, in fact, we might not really be finding it much less with much less iterations. Bottom line here is that linear search, whether we know it's ordered or not, it's still ON. It's still linear. There's still a linear loop here. So from a complexity standpoint, it's no better. But what about runtime? We conjecture that at least runtime should be a tad bit better. So what I'm going to do is inside the run test function, I'm also going to remember the start time. And to be able to do our timing, we've kind of seen the time package once. We have time.time. And when I'm done with all of my searches, I'll do end equals time.time. Right? And now I have an elapsed time. right? Elapsed time equals end minus start. And that's another part of my result. Of course, I can't really return two different things. So I've got a lot of choices here. Maybe I'll return a tuple. Elapsed time and hits. Okay, so I'll return those two values from run test. All right, so I'll call this result. And run test will return it, and I can say result. I guess hits was 1, so I'll do results 1 and results 1, and then I'll say, let's say completed in result 0, found my number of hits. Okay, so let's copy this. All right, let's give that a run. Oops, looks like I missed a plus sign here somewhere. Oh, missed a double quote. All right, so using a small data set, we see what the search times are. Okay, so 1.7 using the linear search times 10 to the negative fifth. 2.26 times 10 to the negative fifth using the linear ordered search. So first off, that should strike you as a little strange. Why is it that one's behaving, the ordered one, the one that's supposed to be taking advantage of some extra information, is actually taking longer? All right, so the first thing you might think of is, well, this is just kind of a weird test case, right? Where that might be a little bit of a special case. So let's take this a step further and take our test a little further. Let's try 1,000 instead. You figure the more samples we do, the more searches we do, if we have some sort of anomaly, if we have, situation where maybe we got lucky in some of in the unordered list or something like that, that should kind of even it out, searching for 1,000. Now I probably get rid of all my printouts, but lo and behold, we are seeing actually the same thing, right? We had 603 successes out of our 1,000, and I'm going to remove that print statement now. But we've got linear search ordered is still taking longer. So let's add 10,000. Let's take this out. We know that we're finding the right things. All right, let's run it. That's going to take some time to complete. It's quite a bit more data now. In fact, the random number generation and the sort is actually taking most of the time. We got linear search coming out at around 7 seconds to search 10,000 times. And we've got 9 seconds for the linear ordered search. At this point, using 10,000 random numbers, we can run this again, but using 10,000 random numbers, we're pretty sure now. It's clear that even though we intuitively, the linear search should be a little slower than the linear search that's using the fact that these things are ordered, we're just simply not seeing that. And those numbers are so close together that I think we can probably safely infer that that's what we're seeing. So let's try to investigate why that is. Here on the left, or down here, we have my code for searching an ordered list, right? So we think this would be a minor win. And one of the things I want to point out here, though, is that even though that this loop goes around probably less number of times because we might return early, we've actually added some steps to our loop, right? We have two comparisons. Let's say I is not, or let's say the key value is not actually in the data. For each miss, for each number where these are not matches, and we're going to continue around this loop, we have two comparisons. And that's compared to the last one where in an unordered or assumed to be unordered list, we only had one comparison. And that's actually coming into play with the timing results that we're seeing. over here, we go around this loop slightly less times. Not exactly half, less than half. It's more than half the number of times because on average, some of the numbers will appear at the end of the list. But even though we're going around this loop less number of times, we're seeing two comparisons over here as opposed to one. That actually goes a long way in explaining why we're getting sort of an unintuitive result. More comparisons per iteration, even though there's less iterations. It's not double the time, of course, because there are a lot less iterations, but it's more time. There's ways to get around this. So for instance, if we look at, here's my implementation of looking through an ordered list and an implementation of an unordered list, we can kind of make some shortcuts here. So let's think about this algorithm over here. Instead of doing two independent checks of the data, what I'm going to do instead is I'm going to check, is I greater or equal to the key? Right? So if we think on the sort of the number line here, right? If I'm looking for 15, is the number greater than or equal to 15? The answer is no for all of these. And if the answer is no, I know that I'm not going to stop, and I know that I haven't found it. Right? Once I find 17, 17 is greater than or equal to the number I'm looking for. 15, if this was 15, 15 would have been greater than or equal to the number I'm looking for. Bottom line here is that if the number that I see inside this list is greater than or equal to the key, I know I'm stopping one way or another. I don't know what I'm returning yet, but I know that I'm stopping. In this code, I'm saying if I find the value that is greater than or equal to the key, I'm returning, and I'm returning not just true or false, I'm returning true or false based on whether the key is equal to I. If the key is equal to I, so if I was 15, I'd return true. If I was 17, I return false. But notice what we've done here now. For a miss, for a value that is not the key, I'm still only incurring one actual comparison. Let's go make that change and we'll see a pretty nice little difference. So I'm going to change this to be greater than or equal to the value, and I'm going to return I equals key. Right, so get rid of that extra call. So let's run this again now. 7 seconds is a long time to wait, so we'll run this once, but we can reduce this number back down to 1,000, so we can run this a little bit more quickly next time. So here we see a significant savings, right? Let's put it down to 1,000 and run this a few times just to make sure that that wasn't an anomaly. All right, so 0.07 seconds, 0.05 seconds. And that's pretty much holding every time I run this program. There's a little variation, but you can see that the difference between linear search with the ordered implication is it's not half the amount of time. It's about maybe about 2/3 the amount of time, roughly around 2/3 the amount of time, maybe even a little bit more than that on average. So this was a nice kind of an exercise to see that, we're not changing the computational complexity here, but we're taking a shortcut in terms of the number of comparisons inside our loop, and it makes a big difference. So 33% savings is a pretty nice result, but it probably isn't as far as we can get. And again, if you remember the last module, you probably know that it's not as far as we're going to get. 33% improvement is still linear search. Both elements are still linear. They reduce the search space by roughly one element, even though the sorted algorithm occasionally can reduce the search space by more when it finds a value that's larger than the key. Okay, so that idea of eliminating the search space by more than just one element, by more than just one index, is something that we can sort of exploit, and we can use that in a little bit smarter way. So the key insight here is that there actually is no reason that we need to start with the first element. We could start anywhere in this list. So let's assume we're going to search for the number 25. One thing that we can do is search in the middle. All right, and so the binary search algorithm is binary in terms of it breaks a list into two different sections, a higher and a lower section of the list. So the first step in the binary search is to skip right to the middle. And we can compute the middle pretty easily. We can just do an integer division of the length and find the middle value. So 11 is not 25. All right, we know that. All right, so we know that element number 6 doesn't have 25 in it. But if we're searching for 25 and we know that this list is ordered, we also know that nothing to the left of 11 can possibly be 25. 25 can't be found there. So without looking at most of them, we've eliminated 7 elements from the search space. And now we can take the rest of this list and we can repeat the same process. So we can skip to the middle of that list and see that 21 is less than 25 and cut out everything to the left of 21. Do it again. 28 is greater than 25. Knock out whatever's to the right of the 28. And then finally, we only have one value left, and we of course find the 25. So we found the number 25 with just 4 searches, with just 4 comparisons, meaning our loop only went around 4 times, and we had a list of size 13. And it turns out that that's actually pretty indicative. That's the average case. That's pretty darn close to the average case for this type of an algorithm. Let's look at the flip side of the coin, where we can't find the actual number, and see how the binary search behaves as well. So again, in the linear phase, in a linear search, or even in the linear ordered search, we're sort of exhaustively scanning through the list. We're going to start out with the same exact way. 11 is smaller than 15. We knock out half. We search the second half, split the middle, go to 21. 21 is bigger than 15. Knock out whatever's to the right of the 15. Go to the middle of the list. 17 is bigger. Knock out to the right. And now we have one element left. 14 is not 15, but there's nothing left to search, so we can definitively say that the key is not in the actual list itself. So it's a pretty simple process, but coding it can be a little tricky. So there's several ways to implement the binary search. You can use a standard loop, or you can use recursion, and I think recursion would be a nice one to look at and to gain some practice in terms of implementing it. And we're going to bake this into our same set of test cases and see what the search time ends up being with binary search. Let's see if it really does feel like it's worth the added complexity that we have. Okay, so before I even do that, like I said, I write a little code and I try to improve it. I was writing my run test program such that it returned a tuple. That was okay, but it's sort of weird, like results 0, results 1. It's not very clear from reading the code what's going on and what I'm actually printing. So instead of doing that, I'm going to create a class to hold test results. So class, let's call it test, and I'm going to have an init. And in my init, I'm going to accept the algorithm that the test is going to work with. And I'll just do self.algorithm. And now my run test, and actually, if I think about it, I can probably pass in all of this data. So let's do that. I'll do self.data equals self equals data. Self.keys equals keys. Inside run test, I'll pass in self. So I'm making run test actually a member method. I don't need anything else because they've already been set. But I do need to add the self here. So my run test is now just becoming a member method. And key's not a member. And start the elapsed time and the number of hits, I'm going to make that a member attribute as well. So I don't really need to actually return anything at this point because I'm just going to allow my test code to print out hits and elapsed time. So let's go down to my main and change this just a bit. I'm going to, let's say linear equals test data keys linear search. Linear ordered equals test data keys linear ordered. And then I will run each test, linear dot run test, and linear ordered dot run test. And then I can print this stuff out. But as I'm moving through this, I notice that I'm going to print out the same thing actually as well. So why don't we change this a little bit and change the design even further and add a member function. Let's call it report. And that'll contain the print statement. And if we look at this, it's just sort of self.elapsed time. Right, that's the elapsed time inside the class. This is self.hits. And linear search, well, that one's a little tricky actually, because that's the name of the actual search. Let's make that a label. Pass that into the beginning of the test. Name, let's say, label. Let's call it name. So that's the algorithm name. And then we'll write using self.name. So the test will know how to print itself or report itself. And when I create that stuff, I'll do linear, unordered. I'll do linear ordered. Okay, and then I'll just say result. Oops, don't need that actually. Oh, I put these in the wrong spot. Sorry. I kept some of my old code around. So I'm running the tests, and then let's get rid of that. I would just call report. And if I look at that now, I've got two tests, and I do the exact same thing on both of them. So I'll get to binary, I promise, but let's just improve this a little bit more. Let's create a list of tests. Actually, I can do tuple. So I'm just going to create a tuple of tests. And let's call that tests. Test.run. Maybe run's a better word. And test.report. All right, so I changed a lot. I should probably check this, make sure it still works before bothering to do the binary. Got a couple small little syntax problems, but it looks like. Data and date, misspelled data. Right up here. Linear ordered is not defined. Linear search ordered. Let's keep going here. Looks like I'm still missing a couple of self references. Yep, self. All right, so I'm kind of transforming the code. It's gradually getting better and better, hopefully. We need self here with the report. And there we go. Okay, so we fixed some of our syntax errors, and you notice if you kind of design your program iteratively, your syntax errors, there might be a lot of them as you transform your code, but they're generally not that hard to find. So I'm still seeing the same difference here. All right, so now on to the binary search. I'm going to create binary search accepts data and a key. Right now I'm going to return false. Okay, and just to show you how easily extensible this program is becoming, data keys binary search. And that's, of course, I need to write the search algorithm. But in terms of the test suite that we're writing, it's actually quite good now, right? It automatically already figured it out. Now, of course, I didn't have any hits because I always return false, and of course, it didn't take much time because I didn't actually do anything. But notice that my main program to add more test cases is actually becoming really easy. And there's other searching algorithms that I might employ later on. These are the only 3 that I'll do in this module. But now this is becoming a much easier to extend. And I'm doing that, of course, through classes, right? Using classes, using functions appropriately. Okay, so let's do binary. So what we're going to do is we're going to say, we're going to define a base case and a recursive case. Remember, binary search is is a recursive algorithm, right? So the idea is identify the base case. All right. So the base case where is essentially where the list that we're going to search is empty, right? There is no value, or there are no numbers in our list. So if length of data is equal to 0, objectively I can say, without doing anything complicated, the value is not here, right? Return false. Else I can return what I'm going to call the result of an internal function. And actually, let's start off with an underscore. And this is kind of a common way of kicking off a recursive algorithm. All right, I'm identifying a base case, and then I'm returning the result of what's really going to be my recursive function. This is a function that is not just going to take data keys, but if you think about binary search starts by searches through a start and an end position. And it's implied when we call binary search that the start position is 0. But if we skip back to these slides, and we look at sort of, one of these midway points, it's not all the time that the start and end point are 0 and some length, right? The binary search is always searching through a list of some arbitrary range within this list. And so the reason I'm going about writing my code this way is I'm going to say, all right, well, if the list is empty, don't worry about it. But otherwise, I'm going to call this new function that I'm going to write. And I'm going to call it with the data and the key, but I'm also going to call it with a start, or let's say a low and a high. And those are indexes, right? The low index to search for and the high index to search for. Right? In the beginning, this is really just, well, start searching at 0 and start and end searching at the last index. And that would be length data minus 1, right? If I had 15 numbers, my last index would be 14. And I'm going to define this binary search function as an internal function to binary, the true binary search. All right, so I've got my, and let's make this a little shorter just so we can keep the code a little separate. Okay, and there's my function. All right, and so this function is actually going to do the vast majority of the work that the binary search method employs. The first thing it's going to do is going to say, okay, am I in a base condition or a recursive condition? And so let's go back to this again. When I got down to the situation where I had one value inside the list, I could do a specific comparison and say whether or not definitively I have the value yet. So it's sort of once you get to a situation where the list is a list of one, you can tell whether or not you have the value. Right? So how do we describe whether a list is a length of one? Well, if the low index 7 is the same as the high index 7. So I'm going to say if high is equal to low, and I'll return whether or not, and it doesn't matter whether I use high or low, that is the actual key. So there's a base condition, right? If my start and end, my low and high index are the same, I'm dealing with a list that only has one value in it, and the answer is, hey, if that one value is the number I'm looking for, I'm done. Otherwise, I need to compute the midpoint, right? So if I've been given a list that is of some length greater than 1, compute the midpoint, go to the middle, all right? And I'll use integer division for that. That's the middle, and I'll see, is the value at the middle equal to what I'm looking for? I'm sorry, I should have wrote E here, right? And if it is, I'll return true. So if we go back to the slides, we're sort of at this condition, right? When we were given a list where we cut to the middle, we found the actual value. Okay, so assuming now that that's not the case, elif, if the value at the midpoint is greater than the value I'm looking for, I need to search left. Else, I need to search right. Right? So I have two different possibilities. Okay, so let's try to attack each one of these possibilities separately. So how would we search the left-hand side? Well, the left-hand side, first of all, what are the indexes for the left-hand side? So we're going to return, we're going to make our recursive call to underscore binary search. We're going to still search for data and key. But what's the low end, right? Well, the low end, if I'm searching the left-hand side, the low end is still beginning at the low end of this list, right? So I'm not really changing that. But the high end is one less than mid, right? So if the midpoint of the list, if that value is greater than E, then really the largest index that this could possibly be at is the one to the left, right? So we're going to do mid minus 1. So that works pretty well. That works in most cases, but we do need to concern ourselves about this integer division. And to see why, let me flip over. I've got a scenario drawn out here. Imagine that we've got this list and we've been looking for the number 29. So at this point, low equals 5 and high equals 6. So we're trying to figure out what to do from here, right? So the midpoint is going to be 5 plus 6 divided by 2. So that's 11. So the midpoint is going to be 5. Right now, that's a case that is a little bit of an issue, because now if we want to go and we determine, I'm sorry, maybe not 29, maybe let's make that 27. If we want to search, if we're searching for 27, 27 is located to the left of this 28, but there is nothing to the left of the 28. We've noticed that the midpoint is actually the same thing as the low in this circumstance. So we got to watch out for that case. When we only have two values in the actual list, we do need to watch out for this low end case. Integer division always rounds down, so we don't have to worry about it if we're going to the right hand side, but if we're going to the left hand side, we do need to worry about this special case. So if the midpoint is the same as the low point, remember we've already checked the midpoint, then just return false. We don't have anything more to do. So before I do this, I'll say if mid is equal to low, return false, else return whatever binary search returns on the left-hand side. Over here, we're just going to do return the right-hand side. And we're still searching data, we're still searching key, but now we are going to begin at an index directly to the right-hand side of mid. Mid plus 1, and high remains the high. Okay. Okay, so let's give this a try. I've already got my test case kind of baked in. Now I'm going to be calling binary search. And I've got sort of a built-in check, right? Because I'm calling linear, and I'm pretty confident that they were working. So the fact that I'm getting 611 back for my binary is very encouraging. Okay, so look at that time, right? So about 4/100ths of a second better than the ordered, about 7/100ths of a second better than the unordered. Let's see how that scales. So let's move this back down to the max to 10,000. We were getting around 7 seconds for the linear search. I think we were getting around 5 seconds or so for the unordered search. Let's see what we get for binary. Okay, so you have to, if you blinked, you missed the pause for binary. The binary search is completing in 15/100ths of a second, compared to the linear and the unordered, the unordered and the ordered versions of the linear search, which is on a measure of a second, 2 orders of magnitude slower. I'm not going to run this for 100,000 values because it's going to take an awful long time. But just to give you an idea, let's actually let's get rid of these and let's just run binary. There'll be a delay because we have to actually, oops, I got bit by that tuple problem, right? I want a tuple of size 1, I got to put the trailing comma. It'll take a little bit of time. That slight glitch was the generation of random values. Let's generate 100,000. All right, so we're generating 100,000. That generation is not included in the actual completion time. You can see for binary, 100,000 values are only 1.97 seconds. And if we continue this, this number is going to grow very, very slowly. Let's see, a million might be a little too much for a recording. Might take a few seconds to generate. Okay, so about 20 seconds, and that's not very, that's not too bad. If we were to run that with a million with the linear, you're probably looking at a few hours to complete. So hopefully that's showing you that the price of what is, undoubtedly a little bit far more confusing algorithm, a far more difficult algorithm to create as opposed to these, the comparison actually is very effective.